Welcome once more to the last class on lectures, semi-free resolution and application. Since this is the last presentation on lectures, semi-free resolution and application, allow me to recall what I have been doing from the first class up to what I did yesterday, so that those who have not attended to the previous classes should understand what follows. So, we consider here consider X a topological space is simply connected topological space and n x k de associated normalized singular quotient. Okay, we saw that nx is a strongly homotopy commutative algebra. With the structure of algebra given by, let me denote it by x equal to alpha nu of x, alpha x composite by omega b, omega m p n of x composite by psi of n x n x. Okay, where our mx here, mb nx is just the morphism of the strongly homotopy commutative algebra that I gave you yesterday. And psi of nx is a morphism, a quasi-isomorphism from to satisfying some condition. This isomorphism satisfies some condition that I gave you yesterday, of course. So, with this, we have on this strongly homotopy commutative algebra, we have on this singular quotient complex the structure of strongly homotopy commutative algebra. This is the first thing that we saw yesterday. So by using this structure of strongly homotopy commutative algebra on Nx, we are going to construct the algebra structure on the Hochschild homology. So this is the first thing that we saw. The second one, the algebra structure on the Hochschild homology. Okay. So yesterday we defined the Hochschild homology of an algebra. Here our algebra is the normalized singular quotient to be the transfer product of define it by to be this. So by taking this composite here, so the map here is the shuffle map. The map here is the section of that I defined yesterday. The map here is the strongly homotopy commutative algebra defined on the normalized singular quotient. So this composite here is what I denoted yesterday by phi. Of course, this composite depends on the section. You know that when you have a surjective map from A to B alpha, this map has more than one, can has more than one section. So this section here, which is the section of alpha of nx, tensor nx is a quasi-isomorphism. So it has a section that we denote by S n x dot S dot nx. So this section is not unique, but all the sections are homotopic. So by moving to going to the homology, we have what? We obtain okay, here we have the homology of phi, and here we have the isomorphism. This is tau. Tau is Quenet isomorphism. So, this is just the Hochschild homology of X. This here we have this, all this is the Hochschild homology of X, tensor the Hochschild homology of X. Okay. So we have here with equal to this composite here, so the product on the Hochschild homology has been given by this relation here. So our H, our homology, Hochschild homology of nx with coefficient in the same nx, end up with our M H X is an algebra. Okay. Now that we have the structure of algebra on the Hochschild homology of the normalized singular complex, we are going to check the link with that homology with the structure of with the Allen-Bemor differential tau. Okay. So, to move to this objective, we will start by defining the structure of algebra on the bar construction of nx with double coefficient on nx. Structure, algebra structure on Bnx, Bnx, Nx, Nx, where here our B is the bar construction that I defined yesterday. Yesterday, to do it, I used a general algebra. Here, I am just replacing the algebra by the algebra of normalized angular quotient here. So, since our mu here, mu x is equal to alpha nx, we define it omega m b nx, composite by our psi nx, our mu here x belong to the isomorphism of differential graded algebra defined from to this morphism is a morphism of differential graded algebra with domain this and codomain this one. But this is isomorphic to the this is just the consequence of the fact that the bar construction and the co-bar construction are adjoint functors. That's why the two are isomorphic. So, to that isomorphism here, to that map here, to map n mu x is in one-to-one correspondence to some maps denote it by mu on G C of Bx Bnx tensor Nx to Bnx. Because the two functors, the bar construction and the co-bar construction are adjoint functors, then we have this bijection here. Since we have this map belonging to this, there exists a map denoted by nu x, so that the two are the last one is the image of the first one through the bijection. Let us denote this bijection by this. So what I'm claiming here is that is equal to mu x. Okay. So, with this, we'll try to construct a bisection on the bar construction with double coefficient in this way. Okay, we have here, recall that the bar construction of nx with double coefficient is just equal to nx tensor the reduced bar construction on the normalized angular quotient tensor. So, here we will just this the left side here, this two first term will be fixed and the last two term will be fixed. We permute the middle here by using the interchange maps. So we have here 1 n x tensor b n x tensor okay, and with this map we obtain this. Okay, now that we have this, we will fix the extremity of this term. That means this one will be fixed and the last one will be fixed. We'll permit this two term and this other two term with this map. And we obtain so through this map we obtain this. And then here we use the shuffle map here. This is fixed. This other one, the first two terms are fixed. The last two terms are fixed. We just apply the shuffle here to to take the bar construction of the tensor product of Nx by itself. So we have here Nx tensor Nx itself, tensor bar construction of the tensor product of Nx by itself, tensor by Nx, tensor itself, and then using this, you use the map nu defined here have here. Here we use the product on this, because this one is an Nx is an algebra, it's the quotient algebra. So we use the product here. Have here Nx tensor B Nx tensor Nx. By using through this map, we have Nx here, tensor here we have our from here to here. We use this map. Nu, our nu x tensor M Nx. So the product on the bar construction with double coefficient of the bar construction on the quotient, the singular quotient algebra with double coefficient in Nx itself is given by this, the composite of the vertical arrow here. We denote that product by M, capital M, B, N star, N star, N star X equal to, equal to M N X tensor nu X tensor M N X composite by tensor nu X tensor, here we have here is tensor here the shuffle map tensor composite by the first one. The first one is this one, and the second one is the other one. Composite by the last map, the first map. So I'm just taking here this composition to say that the product on the back construction of the normalized angular quotient with coefficient, with double coefficient in the same normalized angular quotient is this is the composite of all these maps. So now that we have proved that we have a product on, we have the structure of algebra in the back construction, we will next show that the normalized angular quotient and is so the normalized angular quotient is a n x e bimodule. NXE is just the algebra. I defined it the day before yesterday. The action here are given by the first one for all A in Nx in the normalized angular quotient, B equal to B1 tensor B2 on the enveloping algebra. We have this, have B A dot B is just negative 1 degree of B2 times degree of A plus degree of B1 2 dot A dot B1, and this is the right action, and the left action is given by B is equal to negative 1 B1 degree of B1 times E degree of B2 B2 A B1. One can verify easily that these two relations define the structure of B module on of N star x E the module of this. So on the other hand, we also have that N star x, this enveloping algebra act on the bar construction of Nx with coefficient on Nx as follow. So we have here, we consider here B equal to B1 tensor B2 in the enveloping algebra here, and X, or let's say A0, A1, A2 or 2 up to AK plus 1 belonging to BK of N X N X N X. So the action of this to the left side is given by A0, A2, AK plus 1 is just equal to B1 tensor B2, A0, A1, A2 up to AK plus 1, which is equal to negative 1 gamma B1 dot A0 here. We have here A1, A2 up to AK, and here we have B2 dot AK plus 1. With gamma equal to degree of B2 times summation from 1 to K, degree of EI from 1 to K, negative K plus this one B2, okay, plus degree of E0. Have this. So with this we have the structure of the bar construction of Nx with double coefficient in Nx is a left, the action is a left N X module. Okay. Now you have this. We consider the filtration F K of B to be equal to what? To be equal to Bk of Nx here, K greater or equal to 0. Bk here is indeed equal to have this. So we have a filtration here. So with this filtration, it is obvious that Bn star of x, n star of x, n star of x is the union of f k of that B n star of x, n star of x, n star of x. This means that and this implies that B is a semi-free resolution of Nx, or a this is a semi-free resolution of Nx, or a Nxe semi-free resolution. Okay, so we know that our n, the normalized angular quotient, is a Nxe module, bimodule. We also know that this is a semi-free resolution of our Nx. So we have, from the definition of the Eilenberg-Moore differential Tor, that is equal to this. Okay, we have this from the definition of the Tor, the Eilenberg-Moore differential Tor. We have this. Okay. Now that we have this relation, we can go directly to the link between the Hochschild homology and the differential and the Eilenberg-Moore differential Tor by using this Okay. To deal with this, let us consider the map theta defined from n from the Hochschild complex of the normalized angular quotient to this transduct of algebra. This map, I call it theta, which assigned to any x here cross x1, x2 up to xk, x cross 1, the identity element of the normalized angular quotient x1, x2 up to xk, the identity element of the normalized angular quotient of x. Here, the transfer product is over the enveloping algebra. I claim that this map is a bisection by giving the inverse of that map, not by like this. Theta tilde defined as follow. Consider here x, the cross product, the transfer product is here is over x0, x1, x2 up to x k, xk plus 1. Then we go to have here, the definition is, okay, -1 gamma xk plus 1 a x 0. The transfer product here is over k, the field. Have here x1, x2 up to xk. Okay. It is easy to verify that so our theta is a bisection with inverse theta tilde. Okay. So with this bisection here, I'm moving to the homology. The homology, one has the following relation. this is, and of course you have which are inverse each other. Means that this one is just the Hochschild homology of nx with coefficient in nx. This is the Hochschild homology of the normalized angular quotient with coefficient in the normalized angular quotient. This one is the Eilenberg motor here. So we have a bisection here between these two terms. But we don't know whether this bisection is an algebra bisection or not. So we are going to check whether this bisection is compatible with the algebra structure on each set. Okay. To check it, consider the diagram to check if theta is compatible with the algebra structure on each and respectively. We are going to check if we have this. So to deal with this, let us consider the following diagram. Here we have the Hochschild homology of nx, normalized angular quotient with the coefficient in that normalized angular quotient. We transfer it, we take the transfer product 2 times, and here we have the vector of we take the transfer product 2 times, and here we have the map and you have this. Okay, here we have the isomorphism tau, which is Kenneth isomorphism. With this we obtain exactly And here we have here we also have that Kenneth isomorphism. Down here we have the map here is here we have okay. This is the map that we have here. Okay, and the last map here is just our H star of phi. So from what we did before, this composite here is the product, define the product on the Hochschild homology of the normalized angular quotient with coefficient in itself. This one define the product on the Eilenberg-Moore differential tau here. The diagram, this diagram commute means that this homomorphism is an algebra homomorphism. So the Hochschild homology of the normalized angular quotient of x with coefficient in itself is isomorphic as algebra to the differential, the Eilenberg-Moore differential tau have this. Okay. Now that you have this relation, we'll try to relate, because at the beginning I told you that what we are supposed to do is to show that these are isomorphic as algebra. That's what we are supposed to do by using the semi-free resolution. Okay, I have already proved that. I have already showed the link between the Hochschild homology of the normalized angular quotient with the coefficient in itself with the tau, which is related to the semi-free resolution. Okay, now we are moving to find the relation between the free loop space homology with the Eilenberg tau. We are going to do it, and then next time we'll try to compare the two Eilenberg tau. Okay. Let me take this relation somewhere, because we'll use it. I call it relation 1, okay, as algebra. Now consider the diagram tensor by itself, normalized angular quotient tensor by itself. These are two coalgebra. By taking the tensor product, we still have the coalgebra. And by taking the dual of this coalgebra, we obtain an algebra. And you know that when you have A tensor B, where A and B are modules, there is we have an equivalence here between the dual of the tensor product and the tensor product of dual. That equivalence I denote it by I. Okay. And then the first day, I defined the Eilenberg, the Alexander-Whitney map, defined from N X dot cross Nx to I define this map. So by dualizing this map, we obtain so I have here and this composite I denote it by nu. Okay, so Alexander-Whitney map is a quasi-isomorphism. So the dual is also a quasi-isomorphism. We have an equivalence here, so this composite is a quasi-isomorphism. Now, I will try to show that nx, the normal singular quotient, is a module over this algebra, and the same normal singular quotient is also a module over this algebra. And after that, I will try to show that the identity map is a linear map, from the algebra, from the module over this algebra to the module over this algebra. I said it yesterday. When you have k and k prime, phi, k and k prime are field. Phi is the morphism of field. So, if A is a k module and A prime is a k prime module, a map here f from A to B is supposed to be linear with respect to this relation here. If we have f of alpha A here equal to phi of alpha f of A here, phi of alpha. I said it yesterday. So, I say that n, that this algebra act on nx on the right side by x dot let me call, I defined it yesterday by, I denote it yesterday by this, equal to x copt our new here is the one that I defined here. X belong to this one, and A belong to n normal singular quotient. No, it's what I. Okay. And then nx dot act on the normal singular quotient on the left side by, okay, we have x, we have A, I denote it yesterday by this equal to, we have here n x this is just the cup product defined on the normal singular quotient. This is a diagonal map, so we have this relation. So with this, the normal singular quotient is n B module. In a similar way, we define the action of on the right side by n let me give directly the actions. X equal to x copt x belong here to our x here, and our b belong to this. X belong to nx and b belong to n act on the normalized angular quotient on the left side by what? By this relation b star x equal to what? Equal to copt x. As we did, as I say before, the delta x is just the usual diagonal, topological diagonal, and this sign is the copt product defining the algebraic structure on the normalized angular quotient nx. So with this, we consider the trivial map the identity map. Let's say the identity map. Identity. It satisfies the identity map. Satisfied. The following relation. Okay. So the map we have we had between the and the normalized angular quotient of the cross product was we note it by nu. So And we are trying to prove that this thing as the nx transfer product nx module and this other normalized angular quotient seen as the normalized angular quotient on f of nx cross nx module. The identity here satisfying this relation means that the identity is just a linear map from the first one module to the second one module. That's what we are trying to see. What was we are trying to see here? That this map is a linear map from the module over this one to the module over this one. So with what I say the day before yesterday, we have this relation the map here is nu is a quasi-isomorphism. The identity is trivially isomorphism, means that this is an isomorphism when we move to the Allen-Belmore differential tau. So we have the isomorphism here between these two taus. So this is the next relation that we have. But this isomorphism is an isomorphism of modules, not algebra. Okay, so we have this. Our second relation is this one. Okay. Now to go on with the relation between the free loop space homology and the Allen-Belmore tau, we consider the free loop space and the Allen-Belmore tau. We consider this. Okay, we have here our free loop space. If we discuss free loop space homology. Okay. Let me explain it. Yeah, when I was doing the part concerning the singular homology, I defined the cohomology of I defined the free loop space. I said that the free loop space is just the set of continuous map from the unit cycle to X with a particular topology, with what I call compact open topology. So this is already known. X power I is just the set of continuous map from the unit interval to X, continuous map. I here is the unit interval, means 0, 1. X is our topological space. This is the cross product of this. So, remark that there is a relation between the unit interval with the unit cycle, which assigned to by these maps. Let me call it to bar, which assigned to any t here is the exponential of 2 pi I t. This map is continuous, but it's not bijective. So this map allows one to move from the free loop space to an element here, and conversely, here we have our diagonal here, topological diagonal. Let us denote this map by delta bar, this one by lambda, and this one by lambda bar. Our lambda bar delta here is just delta bar here is just the inclusion map, because when you consider, let me make you understand that a loop is what? A loop is just a map so that the beginning and the end are identified. When you have a loop, you have something like this. So that means gamma of 0 is equal to gamma of 1 when we have a loop, something like this. So a loop is a subset of this. Our lambda bar is just the map defined by gamma of 0 and gamma of 1. So to any gamma here, which is a continuous map from I to X, we assign gamma or the gamma of 0 and gamma of 1. And the other one, lambda, defined from the free loop space to X, we assign to any gamma here, gamma of 0. So with all these maps, this one is obvious. Assign to any x, the couple x, x. So with all these map defined, we can easily check that this diagram is commutative. The diagram is commutative. So having that the diagram is commutative, we apply the quotient functor to this diagram. You know that the quotient functor is a covariant functor, means that applying the quotient functor to the previous diagram, diagram, we obtain the following commutative diagram. So we have here C star of Lx, no, not all fx, of x. Well, let me maintain it in this way. And here we have since the quotient functor is applying the quotient functor to the previous diagram, have this, have this, have this, and we have this. Here we have of delta bar, of lambda bar, of lambda, which is also commutative. And then now I told you the other day that when you have a singular quotient, you have the structure of algebra on that singular quotient of any topological space. So on this singular quotient, we have the algebra structure given by this. This is a coproduct. This is here we have to go there. We have lambda. To go there, we have C star of delta bar. Okay, we have this. So this composite, I denote it by gamma bar. So gamma bar is gamma, not gamma bar. Gamma is equal to product composite by C star of lambda cross transfer product with delta bar of this. Okay. Now taking this cost product over the transfer product. Okay, so we have this. But I told you when we were doing the semi-free, the free resolution and the semi-free resolution, I told you that any free module has a free resolution. So since C star x, the singular quotient of x, is a free module if a C free module, then there exists a, there it has a free C free resolution over what? Over this. And also, when we were doing the free resolution and semi-free resolution, we say that when you have a free resolution of modules, then you can get the semi-free resolution by taking the total complex here. So So we have semi-free resolution here. We can move to the island by motor. So let us denote this resolution by that this map by Scazier isomorphism. We have here gamma that way I have constructed before. This is here I have this the map of the semi-free resolution here. I tensor it by the tensor product here is over this one. Here I have also x. Here you have identity map. So we have something like this. So by moving to the homology, we have this map. Of what? We have homology of the left side. Tensor product here is over this algebra. And then which is just, and here we have this is of course a quasi-isomorphism. And this is an isomorphism. So we have here, because this is a quasi-isomorphism, it's come from here. This is the identity. So we have this a quasi-isomorphism. This is the quasi-isomorphism, means that all this is a quasi-isomorphism. Moving to the homology, you have the isomorphism here. And then we have on the left side here, on the left side here, we have the tau. by definition of the Eilenberg-Moore differential torr, this is exactly the Eilenberg-Moore differential torr. So we have this. With this isomorphism, we have that torr of to the free-loop-space homology as module. Okay. This is the third relation. But before putting it here, let me give another explanation, another clarification on this isomorphism. We have this relation. We have the torr of is isomorphic to which is isomorphic to, and this one is isomorphic to the last isomorphism comes from the last isomorphism comes from the fact that the normalized singular quotient of x is quasi-isomorphic to the singular quotient. We saw it when I read the short exact sequence containing these two terms. So this is a quasi-isomorphism. So we have with this, it means that of this cross product is quasi-isomorphic to this cross product. Have a quasi-isomorphism here. We have here the quasi-isomorphism. Applying it to one of the propositions that I gave you on the differential torr, we have this relation here, this isomorphism here. And now here, just consider here, of course, we have the identity here. Because we have the identity here. We still have the identity here. But here, we have this map. Have a map from x to xi. Xi, I say it is the set of continuous map from I to x, which assign to any x a gamma continuous map from this, so that gamma of 0 equal x. And then taking this map, putting here the functor, the quotient functor, we obtain something like this. Let me call this map it is not obvious, but we have to do some computation here to prove that this map is also a quasi-isomorphism. so that this, we have this isomorphism here as module. Here as module. So this is isomorphic to this as module. This is also isomorphic to this as module. So finally we have this isomorphic to this as module. So our free loop space cohomology is isomorphic to this as module. This is the test that relation. This is the third relation. Okay. Now that we have the relation between the Hochschild homology and the tau here, this relation, the second relation and this one, remark that this one, in this relation, this term is exactly this one. So with 2 and 3, we have that the free loop space cohomology of X is isomorphic to the tau of to the tau of Nx cross transfer product Nx, Nx, Nx. Have this 2 and 3. So now to move to the bijection that we want to prove, we just have to prove that this transfer product is isomorphic to this other transfer product. And to do it, we will consider this algebra. So show that the Hochschild homology of the normalized angular quotient of X with coefficient is isomorphic to the free loop space cohomology. We just have it is to show that isomorphic to just have to show this. But we have the identity map from here to here, from here to here. So I just have to construct a map of algebra from this to that, an isomorphism. Okay. So let me construct this map. Consider the map. Phi defined from the I defined it from this nx to n up like this, which assigned to any f here. Phi applied to f, which is a map from n star to n star to k, n star of x, of course, to k. such that for any n simplex here, we have phi of f applied to sigma n is equal to f of sigma n composite by 2n, where 2n is equal to, is a map from the n standard simplex delta to the same n standard simplex delta, which is assigned to any element in this Ti, Ei, we assign Ti, E, n minus I. So this is how our 2n is defined. Okay. Obviously, 2n is a homeomorphism. The topology here is the one, is induced from the topology of Rn plus 1, same thing here. So this map is an homeomorphism. Moreover, we have phi composite by itself applied to f, applied to any sigma is equal to f of sigma n. Means this is for all sigma n belonging to n star x. Means that phi composite by itself applied to f is equal to f. That is phi composite by itself equal to the identity of our n star here. Means that our phi is a bijection. And then I still have to prove that phi is a morphism of is compatible with the algebra structure here and here. To show that phi is compatible with the respective algebra structure, consider the maps, the affine maps lambda bar p defined from delta p to delta p plus q. Of course, p here and q are in n integers, which are assigned to summation from 0 to p ti ei, summation from 0 to p plus q ti ei, with ti equal to 0 if I is greater than p. And lambda child here, q, defined from delta q to delta p plus q, is assigned to any element here ti. This is equal to, let me put here, it's okay, from 0 to p plus q equal to t j e p plus j, with t j equal to 0 if j is greater than q. So using these two maps, we will show that our phi is compatible with the respective product on the domain and codomain. So you consider here f in n p of x and j on n q on of x. We have here phi of f copt j applied to sigma of p plus q is equal to what? Is equal to, according to the definition that I gave you here, is equal to f copt g applied to sigma p plus q composite by t p plus q. Is equal to what? Equal to -1 p q f of sigma p plus q composite by tau p plus q lambda bar p product with f, no, not f, is j of sigma p plus q composite by tau p plus q lambda child q here. The product here is the product in K, because these two maps are taking the value in K. So we have here, this is -1 p q f of sigma p plus q lambda child p tau composite by tau p j sigma p plus q composite by lambda okay, it's by lambda q composite by 2 q here. It's okay. Okay. This is equal to -1 p q. Since our field is commutative, so and this term are the term of K field. Okay, I can permute these two terms. So I have here j of sigma p plus q composite by lambda bar q composite by 2 p composite by dot f of sigma p plus q lambda child p tau p. Okay, have this. Okay. But this is equal to -1 p q phi of j copt phi of f applied to sigma p plus q here. And this is, remember that when you have the opposite algebra, the product in the opposite algebra denoted by this, when you have A dot B is equal to -1 degree of A, degree of B dot A, something like this. I say it at the beginning of this course, of these lectures. So we have here -1 p q times -1 p q. Here we have phi of f cop bar phi of j applied to sigma p plus q. The cop bar here is just the product on the opposite algebra here. So this is this and this product here is just 1. So we have here phi of f cop bar phi of J applied to sigma P plus Q for any sigma P plus Q belonging to n P plus Q of x means that phi of f copt j is equal to phi of f cop bar phi of j, and that make us see that our phi is compatible with the product. So phi is an algebra homomorphism. Okay, now that we have shown that phi is morphism of algebra, we just have to tensor it by the identity and then we have something from tensor n x to n x tensor n x opposite algebra here, which is this two product here is the enveloping algebra here. And I have finished. So we have as module here. So we have proved here that this is the Hochschild homology. The left side is the left side is the left side, yes. The left side is just, this is the Hochschild homology. Hochschild homology. The left side, this is the pre-loop space cohomology, because this is isomorphic to that, and this from this relation, these two are related. That means the final relation that we have here is Lx isomorphic to I call it 3 prime. Okay. So we have this isomorphic to this is the one that we have here. This isomorphic to this is the one that we have here. So we have proved that as module that the two are isomorphic through the Eilenberg-Mortor differential term. So through the semi-free resolution, because that Eilenberg-Mortor has been defined using the semi-free resolution. This is an application of semi-free resolution to the topological case. But in fact, these results has been extended by which we haven't only showed that this is a module of isomorphism. We have extended the relation by showing that this is an algebra isomorphism. So we construct here a product and a product here, and we show that the two products, this isomorphism is compatible with the two products. That's what we did here. At the Okay. With this diagram, this arrow here, the vertical arrow, define the product on this Allen-Bay motor. This arrow here define the product on this Allen-Bay motor. This arrow here define the product and what we call it in French, product intermediate. Yes, and then this one define the product between the previous one and this one here, because this one is exactly what we have here. This one here, that's the one we have on the left side here. So we have the product between the product on this algebra and the product on this module and the product on this module. And with this diagram, since this diagram commute, means that the morphism here is compatible with the product. And then we have shown that the two modules are not isomorphic as module, but they are isomorphic as algebra. Okay. So by this, we have proof. We have tried to give a new proof of John's isomorphism by using the semi-free resolution, by giving an application of semi-free resolution to the topological case. Okay.